Okay, so now we're going to move into the new stuff for this semester. We're going to talk about entropy. Okay, you've probably heard of entropy before, and entropy is normally described as a measure of disorder. So we start with the first law of thermodynamics. Um, Energy cannot be created or destroyed, right? You can't make your own energy, right? You've got to, the only energy is what is being converted, right? And so the total energy of the universe is not changing, but it can be transferred. And it can be transferred to the system and to the surroundings. And remember, we just talked about that in Gen Chem 1 and in the refresher that I just did. Turns out that even the transfer of energy is going to have a problem with it, right? So you're not even going to break even. If you want to recharge a battery with 100 kilojoules of useful energy, it's going to require more than 100 kilojoules. And that's due to the second law of thermodynamics. So every energy transition results in a loss of energy, or this energy tax, if you will. And that means that something's lost to the surroundings by heating it up. So you think about kinetics, the rate of reaction. We talked a lot about that earlier. Diamonds going to graphite is a very slow process, right? It is, in thermodynamics terms, though, it is a spontaneous thing. Why is it considered spontaneous? Well, it's because on this side, these are more highly ordered than on this side, right? So spontaneity favors the disorder. So we got to talk about a spontaneous process, because spontaneous processes occur because they're going to release energy from the system. And most of these proceed from a system of higher potential to a lower potential. That means that there's an exothermic enthalpy coming off, right? But there are some spontaneous processes that do proceed from a system of lower to a system of higher, and those are considered endothermic. So how can something absorb potential energy yet have a net release of energy? So let's look at ice. Melting is an increase in entropy, right? You know that the fixed position of the water molecules in ice allows less motion. And at 0 degrees, this is a spontaneous process. So there's more freedom of motion from the ice where it's fixed and to a more random liquid water. They're closer together, right? But they're not as fixed. So when systems become more random, energy is released, and that energy is in the form of entropy. So two things that affect whether a reaction is spontaneous. The two things are enthalpy or entropy. And enthalpy is delta H, and remember it's that difference in the sum of the internal energy. So it's PV work, pressure volume work, energy of the reactants to the products, right? That difference. Entropy, right, is the difference in randomness of the reactants compared to the products. Okay, so looking back at enthalpy, delta H is generally measured in kilojoules per mole. Stronger bonds mean that we have a more stable molecule. So a reaction is generally exothermic if the bonds in the products are stronger than the bonds in the reactants. So that means that energy is released. It means delta H is negative. And generally, it's endothermic if the bonds in the product are smaller or are weaker than the bonds in the reactant. So endothermic is where energy is absorbed, and delta H is positive. The enthalpy change is favorable for exothermic reactions and unfavorable for endothermic. So entropy is this thermodynamic function, and it increases as the number of ways in which things can arrange increases. Okay? So S is entropy, right? And it's generally described in joules per mole. Okay? Remember, enthalpy was kilojoules per mole, so enthalpy is the bigger factor. But this S can be broken down into, first of all, Boltzmann's constant, which we use in a lot of different equations, but then the natural log of W. W is the number of energetically equivalent ways a system can exist. Kind of referring back up to that definition at the top there, right? The more ways that it can exist, right, the larger W is. Random systems require less energy than ordered systems, and so they have more ways that they can exist. So energetically, it does not matter whether we're in state A, state B, or state C. But one of them is more probable than the other two. So I'm not going to get into this macro state versus micro state, but the macro state of where there are two molecules in each container, right, is the one that we were just talking about in that previous slide. So again, this idea of macro states and the probability, that's why it went to that micro state. Basically what it's saying is that there are only, there's one possible arrangement that gives A and B, but then if you number the four molecules, you get actually 6 different ways that this can exist. Therefore, right, it has a higher randomness. So we measure entropy as a change at delta S, and so we take the final minus the initial. And so entropy is favorable when delta S is positive, meaning that the final, right, is more disordered than the initial. So increasing in entropy, what can cause this? Reactions where the products are in a more random state, right, a solid versus a liquid or a gas. Reactions that have larger numbers of product molecules and reactant molecules. Increases in temperature, that's an important one. And solids dissociating into ions when they dissolve. So back to the increase in entropy for ice going to liquid water, right? And that's actually tied to the motion, the ability to move. So that ability to be more random that we saw in the case of liquid water versus ice. A delta S of a system is, when it's positive, that means that it's favorable. The entropy change is favorable for the process to be spontaneous. However, when the system is negative, delta S of the system is negative, that means it's unfavorable, right, for the process. And so we can go back to a form of Hess's law and now say that if we can go to the standard enthalpies of each of the reactants and each of the products, and we can take the summation of the standard enthalpies of products minus the summation of standard enthalpies of reactants and add all those up, we can get to the delta S of the system. So revisiting this macro state thing, right? Change of states, the number of macro states it can have changes, and so the more degrees of freedom, the more the molecules can move, the more macro states are possible. And so solids have fewer macro states because they're in a more fixed position, but liquids have more macro states, and then gases have even more macro states. So as you go from a solid to a liquid, right, you're increasing the motion, the macro states. As you go from a liquid to a gas, you're increasing them again, and the temperature is going up, right? So the kinetic molecular theory is involved. Okay, so these these answers are already in here, but you want to predict whether the delta S of a system is positive or negative. You drop a glass, it shatters, it's now in a bunch of pieces. That's more random. Delta S is positive. Water vapor condenses, that means it's going from a gas to a liquid. The delta S is negative. When oil and vinegar in the salad dressing separate, they're no longer dispersed, so that delta S is negative. When you dissolve sugar in tea, though, that sugar is going from a solid into a solution. Delta S is positive. We look at this lead oxide, and there are more molecules on this side, 3, so delta S is positive. There are 4 versus 2, delta S is positive. There's 1 versus 2, delta S is negative. So we do have to touch on the second law of thermodynamics, and it basically is saying that the total entropy change of the universe is going to be positive for a spontaneous process. But for a reversible process, the delta S of the universe is 0. Irreversible or spontaneous processes, the delta S of the universe is going to have to increase. And so the delta S of the universe is equal to the system plus the surroundings. If the entropy of the system decreases, then the entropy of the surroundings must increase by a larger amount, right? Because the delta S of the universe has to increase. So when the delta S of the system is negative, the delta S of the surroundings must be positive and big for a spontaneous reaction. So this is all leading up to kind of combining things to figure out how we determine spontaneity and spontaneous reactions. So basically, in the universe, right, the delta S for life is spontaneous, right? All of this goes from the newborn growing up into the graduate and eventually, an adult with another newborn. All of that is spontaneous in terms of the chemical processes. So now this second law says that entropy of the universe is going to increase for a spontaneous process. If a process is spontaneous and the entropy change is unfavorable, there must have been a large increase in the entropy of the surroundings. So again, just kind of reiterating, entropy change in the system is unfavorable, right? Here's the system, unfavorable. The entropy change in the surroundings has to be favorable, right? And large to allow it to be spontaneous. Back to standard state, standard conditions. Gases, pure gases, exactly 1 atmosphere. Solids are liquids, pure solid or a liquid in its most stable form at exactly 1 atmosphere. And then solutions, right, of 1 molar concentration. Those are all standard states. So the third law, right, or absolute entropy. So the absolute entropy of a substance is the energy that it has from that dispersion, that motion, right? The third law says basically that the only time there is no entropy in the system is a perfect crystal formation at absolute 0. Then the absolute entropy can be 0. That means that every substance has a positive entropy. So this standard absolute entropy, right, this S0, means that entropies for 1 mole at 298 for any particular state, allotrope, molecular complexity, molar mass, and a degree of dissolution, right, is something we call extensive, right, meaning that it only depends on the state of that substance. Here's a list of a bunch of standard molar entropy values, right, and you recognize this as similar to our standard enthalpy values. In other words, We could use these as the building blocks to determine the entropy of a reaction. So it stands to reason here that the gas state is going to have a larger entropy than liquid at a particular temperature, and that the liquid state is going to have a larger entropy than the solid at a particular temperature. So this idea can be extended. Relative standard entropies and molar mass, the higher the molar mass, right, the larger the entropy. This is because the bigger these atoms are getting, the closer their energy states are, and it allows more dispersal among those energy states. So we talked about allotropes early on, and we had an example of two different allotropes of carbon. The first one is diamond, and the second one is graphite. So the less constrained, right, is going to have larger entropy. So graphite is less constrained, and it has a higher entropy. So in general, complexity adds to entropy, and so the more complex molecules are going to have larger entropy. That's because there's more available energy states. They can move around more, right? There's more bonds. There's just more to it that can be that can move. So dissolved solids are going to have larger entropy because, again, they're moving around more. They're distributed throughout the mixture. Okay, so now we get to this idea of when we can look at the delta S of a reaction, right? And Hess's law. So we can extend now Hess's law to entropy and say that the delta S of the reaction is equal to the summation of the products minus the summation of the reactants. Very similar to the delta H of formation. And we know that there is a specific temperature involved. It's 25 degrees C. So calculate the delta S for a reaction, right? Here we've got ammonia reacting with oxygen, and you get nitrogen monoxide and water out. And we've got all the substances listed over here. Their standard molar entropies. You set up the reaction or the equation of delta S is equal to the products minus the reactants, summation of them. Here are all the products, including the stoichiometry. Here are the reactants, including the stoichiometry. You get to this 178.8. It's a positive, right? You might expect that because you have 10 molecules of gas on the right side versus 9 on the left side. What about entropy going from H2 plus O2 to H2O as a gas, right? When you do that calculation, again, set it up, look at the products summation minus the reactant summation, and you're going to get there. And here it is, it's this minus 88.7. You would expect that because you've got 3 moles of gas going to 2 moles of gas.